One man's. It is 1914. You are a chemist. Does your loyalty lie with the periodic table or with the flag? Did you know that a single chemist created the tool to feed billions and then forged the weapon to kill millions? Fritz Haber was that man. He cracked open one of the strongest chemical bonds in nature, the nitrogen triple bond, unlocking an era of infinite fertilizer. This is only the first of Haber's paradox, because while ammonia shines like a modern magic lamp, essential for life-saving bread and death-dealing explosives and precursing poison, it is also a mirror. It reflects the soul of the man who tames it. Today, we unfold the story of two chemicals, ammonia and acetone, and the two men who unleashed them. A journey through moral duality across three realms: science in war, man and nationalism, and the struggle for identity. This is chemistry forging civilizations where molecules find purpose, and chemical reactions shape history. Chemistry, the science of transformations, has changed humankind. A controversial Nobel Prize. The 1920 Nobel Prize ceremony was anything but ordinary. For years, the Great War had silenced the awards, but as the world attempted to move on, Stockholm prepared for a massive resumption honoring all the laureates of previous years as well. The spotlight fell on the 1918 laureate in chemistry, Fritz Haber. He was honored for the synthesis of ammonia, NH3, from its constituent elements nitrogen and hydrogen, a breakthrough achieved between 1905 and 1913 that promised to feed a surging global population. Ammonia is the precursor for the synthesis of fertilizers and several explosives. An acute lack of adequate supply of ammonia has been felt for several decades already. It is estimated that world population grew 60% during the course of the 19th century alone, but the whole was filled with shadows. Haber's award stirred a virulent controversy. It wasn't because ammonia could be turned into explosives. It was because the man standing on that stage was seen by the world as the father of chemical warfare. For many, the hands receiving the world's highest honor were still stained with the chlorine of the trenches. Leading the Kaiser Wilhelm Institute for Physical Chemistry in Berlin, Haber participated actively in World War I, developing and even administering poisonous chlorine gas at the Ypres front and in the Eastern Front as well. He was there, directing both at the laboratory and at the administration of the poison in battle, making decisions and taking notes. Many scientists of the time believed he had crossed a moral line. Numerous colleagues skipped the Nobel Prize ceremony. Some refused to even shake his hand many years after, the most notorious being Ernst Rutherford, the discoverer of alpha and beta radioactivity. In his defense of his wartime actions, Haber claimed that death was death, by whatever means it was inflicted, emphasizing the relative scale of injuries between gas and shrapnel. He also used other psychological and legalistic arguments. Albert Einstein said of him, "One of those personalities who are bigger than their work, tragic in their greatness and their failings." Before progressing, I am curious, what do you think of Haber's wartime decisions? Was Haber a patriot doing his duty, or a scientist who betrayed humanity's trust? Does the food he provided for billions cancel out the gas he unleashed on thousands? Share your thoughts below, because as we're about to see, there is a wider moral dimension to this story that chemistry alone cannot solve. Ammonia, the magic lamp of modern age. For centuries, farmers faced an unpredictable gamble. Farmers struggled to exhaustion with fields limitations. Some soils had limited food producing capability. Soils wore out, became depleted, and crop yields dwindled due to reduced fertility. Yield of some crops was limited because soils were unsuitable for certain crops. Humanity tried everything: crops rotation, relocating, the practice of establishing a sabbatical on the ground, a fallow field practice every 7th year, like established in the Old Testament. Slowly but steadily, humanity learned to use materials to enrich the soil: manure, products of vegetal and animal decomposition, etc. Then emerged guano. By the 19th century, guano was used universally as the go-to source of nitrates. This natural fertilizer, found in places visited by millions of birds, is the result of the accumulation of bird droppings over centuries. Rich in nitrates, was obtained mainly but not exclusively from the coast and islands of Chile and Peru. Rich in nitrogen, guano can be used as is or industrially processed for increased efficiency. Yet, guano is finite and vulnerable to supply issues, distance and armed conflict, like the one fought by Chile with Bolivia and Peru over this same resource. In 1898, the world was given a deadline. Sir William Crookes warned that civilization was on the brink of starvation. He issued a desperate challenge to the chemists of the world: fix nitrogen or watch the world burn. 10 years later, Fritz Haber answered. Chemists began to dream. Could we produce ammonia ourselves? With air consisting of 78% nitrogen, but it is locked in a bond so strong that it is useless to us. Sure, there is a way to harness that. A steady supply of ammonia would transform agriculture. It could be used as the precursor of all the nitrogen-containing products that agriculture requires. Urea, one of the most widely used fertilizers, ammonium phosphates, ammonium nitrate, or ammonium sulfate. All these fertilizers rely heavily on a steady supply of ammonia. A staggering 80% of the ammonia produced worldwide goes into fertilizer production. But as the Haber process was perfected, the world caught fire. Nations swiftly adapted the new knowledge to produce explosives: ammonium nitrate, nitroglycerin, from which dynamite and cordite are produced, nitrocellulose, trinitrotoluene, TNT, etc. The production of these explosives required large quantities of nitric acid, HNO3, which was produced also from ammonia by its catalytic oxidation at 800 to 950 degrees Celsius using the Ostwald process. Suddenly, chemistry wasn't just confined to the fields, it was in the trenches. Ammonia from thin air, the wonder of the Haber-Bosch process. Picture tackling a bond stronger than steel. That was the challenge facing chemists, but Fritz Haber prevailed. Synthesizing ammonia, NH3, is notably difficult. The nitrogen molecule N2 is notoriously unyielding due to its robust nitrogen-to-nitrogen triple bond holding the atoms tightly together. With an energy of 941 kilojoules per mole, fortunately the air is full of it. 78% of the air we breathe is nitrogen, if only we could tame it. Haber delved into the dynamics of the reaction equilibrium for the formation of NH3 from the gaseous constituents nitrogen and hydrogen. N2 gas plus 3 H2 gas yields 2 NH3 gas. Delta H equals minus 92 kilojoules per mole, tackling the battle of the extremes. On one side, the enthalpy of the process is negative, which means it is exothermic. It releases heat and as such is favorable from the caloric point of view. However, we are taking 4 chaotic gas molecules and forcing them into 2, creating order out of chaos. But nature resists order. The result is a shrinking in the entropy of the system, which is a way of saying that there are less ways in which the particles can be arranged, so that at high temperatures the free energy of Gibbs, delta G, will become positive and the reaction stalls. Haber turned to the Le Chatelier-Brown principle. If a change of condition, such as pressure, temperature, or concentration, is applied to a system at equilibrium, the system will shift in a direction that counteracts that change and re-establishes a new equilibrium. An increase in pressure should have a similar effect, since 4 moles of gaseous reactants are converted into 2 moles of gaseous product. So, what is a good chemist to do? How is this tug of war solved? High pressure wants to squeeze the gas into ammonia. Low temperature wants to keep the yield high. But low temperature makes the molecules too lazy to move. So far, so good. But then we have to address the important matter of the speed of reaction, the kinetic effects. Surprisingly, an increase in temperature should enhance the rate of reaction since it leads to more collisions between molecules. But the nitrogen bond is stubborn. It refuses to break. So a catalyst is needed, something that will help break the triple bond in nitrogen and force it into forming ammonia. Haber succeeded to prepare small quantities of NH3 in the laboratory, but to achieve industrial production levels, he partnered with the BASF chemical company. Thus, the Haber-Bosch process was born. In this endeavor, iron appeared as the unsung hero here, a catalyzer that would reduce the energy of activation of the reaction. We'll revisit that in a moment. Preparing the raw materials. Have you ever wondered how large industrial plants source nitrogen for ammonia production? Drop your thoughts in the comments to showcase your knowledge. Nitrogen is obtained by fractional distillation of liquefied air after filtration of impurities like water vapor and CO2. If you understand how fractional distillation works, let me know. Fractional distillation is based on the different boiling points of liquid nitrogen, argon, and oxygen, the main constituents of filtered air. Since the difference in their boiling points is correspondingly minus 196 degrees Celsius, minus 186 degrees Celsius, and minus 183 degrees Celsius. By gradually heating different areas of the fractionation column, it is possible to obtain pure nitrogen. The main sources for hydrogen for the Haber-Bosch process are from steam reforming of natural gas or by electrolysis of water. Natural gas, mainly methane C, H4, must first be cleaned of sulfur compounds by a catalytical process. Then it is heated with water at high temperature to produce hydrogen and carbon monoxide, CO. This is eliminated in turn at lower temperature, converted into carbon dioxide, CO2. Both carbon oxides are brought down to parts per million, ppm level, by the extraction with amines or solvents. Clean hydrogen can now be fed into the Haber-Bosch process. What is really the role of a catalyst in a difficult chemical process? Drop your thoughts in the comments. I'm interested to know, and I read all the comments. The selection of catalyst is critical if Haber-Bosch is to use achievable temperatures and pressure. The catalyst should be able to lower the energy of activation of the reaction, which in this case means easing the breakage of the nitrogen to nitrogen bond and make the nitrogen single atoms available to bond with hydrogen. It should have a large surface area, meaning multiple contact points for the reactants to attach themselves to. For many years, grinded iron pellets of iron 111 have been the choice. Now let's dive into a little bit of crystallography. Iron has a body-centered cubic BCC structure. Crystallographers assign the notation 111 to a cut of the BCC structure trough, a plane that cuts space through the three axes XYZ at equal distances. When using such cuts as a catalyst, they provide a compromise between the reactivity and the number of iron atoms that touch the plane, that is, the packing density of the atoms in the lattice. The densest plane is 110, which includes the atom at the center. In this plane, the atom packing is highest. Why then prefer the less dense 111 plane? Because too much packing blocks access of nitrogen molecules to the active sites. The plane 111 strikes the perfect balance, enough atoms to react without atoms that block access. At the atomic level, the reason iron is well suited to catalyze the Haber process is in the ease by which iron can share an electron from the incomplete d orbital level 3d6. The nitrogen molecule has 10 electrons in bonding orbitals and 4 electrons in anti-bonding orbitals. The bonding orbitals have lower energy than the atomic orbitals they derive from. The anti-bonding orbitals instead have higher energy. The nitrogen molecule has 6 paired electrons, more in bonding orbitals than in anti-bonding. The order of chemical bond in the molecule is 3, or a triple bond. The iron atoms have those 3 unpaired electrons in the 3d orbitals. One of them can be shared with the pi asterisk antibonding orbital of the nitrogen molecule. This reduces the order of the nitrogen to nitrogen bond. The bond with iron is strong enough to permit the breakage of the nitrogen to nitrogen bond at the temperature of the process, but not strong enough to retain the formed ammonia irreversibly. The compromise conditions for the Haber-Bosch process are 200 atmospheres and 450 degrees Celsius. The process typically achieves 10 to 25% ammonia per pass. When the unreacted gases are recycled, the overall yield of nitrogen conversion exceeds 98%. In the cyclic process, the effluent NH3 is liquefied and the unreacted nitrogen and hydrogen are separated and reintroduced. After each cycle, the reactor is slightly purged to avoid buildup of residual methane from the hydrogen supply and residual argon from the nitrogen supply. And so, the Haber-Bosch process was crafted, a scientific triumph, a pivotal moment for civilization. Current improvements to the process yield about 30 to 40% per pass. Chemistry and War, a tale of ethical decisions. For Fritz Haber, it was only the beginning of a moral whirlwind involving chemistry, war, social status that would leave him nationless. This is the story we are now about to tell. The moral whirlwind of Haber's legacy did not stop at ammonia. The same research group that mastered the air also mastered the art of destruction. In the 1920s, Haber's team developed Zyklon. Its active soul was hydrogen cyanide, or HCN, of which ammonia is a precursor. Chemically, HCN is a masterpiece of efficiency and a nightmare of biology. It is a small, volatile molecule that targets the very engine of life. By strongly binding to the iron in our cells' enzymes, it halts cellular respiration. It produces the infamous iron cyanide carmine complex, iron CN63-, which suffocates the body not by removing air, but by making it impossible for the body to use it at the molecular level. While Haber was prying nitrogen from the air in Germany, another chemist was looking at a different kind of alchemy in a laboratory in Manchester. His name was Chaim Weizmann, and he had a diametrically opposite moral standing. Where Haber used high pressure and iron to force nature's hand, Weizmann used something much more delicate, life itself. Weizmann harnessed Clostridium acetobutylicum to turn molasses into acetone, the lifeblood of the British cordite supply. Enter acetone. In Britain, at the same time, there was a lack of acetone, a solvent needed for the preparation of cordite. Since the late 19th century, cordite substituted gunpowder in guns. It is the smokeless propellant used from rifles to artillery shells and everything in between. It is a mixture of nitroglycerin and nitrocellulose with petroleum jelly. Using acetone as a solvent allows the mixture to be made into a colloid. This means the components are very finely dispersed in the acetone. When the acetone evaporates, the mixture can be extruded as cylindrical cords, which are then used as an almost smokeless propellant in guns. This best solvent is, yes, you guessed it right, acetone. In the war years, wood imports to Britain stalled, leading to an acute lack of acetone. An alternative needed to be found urgently to the regular method of dry distillation of wood. Chaim Weizmann, originally from Russia based in Manchester, solved the problem by developing a method based in the anaerobic fermentation of molasses and starches with a bacteria called Clostridium acetobutylicum. The process requires stringent control of acidity measured as pH and complete absence of air. Following this discovery, Weizmann became known as the father of industrial fermentation. Winston Churchill, First Lord of the Admiralty at the time, immediately embraced the solution and ordered numerous facilities to produce acetone to be set up, first in Britain and later in Canada and India. He appointed Weizmann as head of the Admiralty laboratories from 1916 to 1919. Both men faced a critical moral question separate from the role of chemistry in war. What if you lived as minority, between a people that only merely tolerates you? Would you change your own people, put aside your cultural heritage, who you really are, to be accepted by a society that despises the likes of you? Fritz Haber was Jewish, as were many scientists in Germany at the time, Albert Einstein among them. Haber was madly ambitious, and in the atmosphere of Germany, France, and other European countries, Haber faced many social barriers. Post-French Revolution, Napoleon granted Jews citizenship in the new entity birthed from the Revolution, the French nation. Napoleon abolished all restrictions on Jews. No more prohibition preventing Jews from having a profession or owning land, hoping they would become useful citizens and lose their distinct national identity. He did the same at any place his armies reached, but that was just in paper. Jews are an antique people with an equally antique culture, a common historical conscience dating from the time of the collapse of the Bronze Age, as well as a continuous longing for the lost ancestral homeland in the land of Israel. The nations of Europe insisted that they convert to Christianity in order to accede the higher positions and be accepted in society. Some did, like Haber, many did not. Haber fully embraced German nationalism and used his knowledge of chemistry to help Germany in World War I. It was not only the production of ammonia, but also the direct development and use of chlorine gas in the actual battlefields. He led his institute's research into the development and use of poison gases in general. Chaim Weizmann was also Jewish, but he remained loyal to his people and active in the liberation movement that was fighting for the return of the Jews to the ancestral homeland, in stark contrast to Haber. Haber's wife, Clara Immerwahr, herself a chemist, also a converted Jew, was a staunch pacifist that took her own life shortly after her husband led the first gas attack at Ypres. What is your opinion on the role of science in warfare? Should chemists contribute to the creation of weapons? Does urgency or the threat of annihilation have any bearing on a possible decision? Share your thoughts in the comments. Fritz Haber's exceptional service to Germany was repaid by forcing him to resign once the Nazis raised to power. As a Jew, holding office was impossible. He left Germany in a hurry, stayed for a short time in Britain in 1934. At this juncture, Weizmann offered him the position of director of the Daniel Sief Institute of Science, which he had recently established in the land of Israel, which Haber accepted. He died in Switzerland on his way to assume the position. Haber sought a home in a nation, Germany, that eventually spat on him and spat him out, while Weizmann used his chemistry to rebuild the home for a nation that lost it 2 millennia ago in the hands of the Roman Empire. The Institute of Physical Chemistry, which Haber had to abandon in a hurry, continued his research in the subject of gas warfare. Eventually, they developed the gas used to kill millions of Jews and others, Haber's family among them. By contrast, Chaim Weizmann's acetone venture ensured the British government Balfour Declaration, stating the government's support for the establishment of an independent Jewish state in the land of Israel, which became the present Israel. The Sief Institute he founded would take in later years the name of the Weizmann Institute of Science and become one of the leading scientific institutions in the world. The Haber-Weizmann paradox. Chemistry was used to advance German interests, British interests, and Jewish interests. One man thought to change his identity in a futile, tragic pursuit. The other fought for his people, became the first president of Israel, the rebirthed Jewish nation. Is a scientist's primary loyalty to the state that funds them, or to the humanity that their discoveries will inevitably affect? Our exploration surfaced profound moral dilemmas within science and on a personal level, illustrated through real lives in genuine circumstances. Enjoying our project Chemistry Forging Civilizations? Subscribe and comment. We value your insights.